Kia ora tātou. Ko te piha te maunga, ko Waitemata te moana, ko Jumbo Jet te waka, ko tangata tiriti, ko Martyn Nash te moana. Thanks for Martyn for inviting me to give you a little bit of a talk about something that really gets me wound up and really passionate about. Before I do that, I just want to get a sense of how many people in here have heard of the heart. Can you put your hand up? Put your hand up really high. It makes the heart symbol if you really know what you're doing. Just one sec. I just got to get my camera out because I know I'm in a friendly audience and we know which is the best organ in the body. Thank you. So the other thing I want to tell you about is this picture up here. This is a heart of a big blue whale. It was found in the north of Canada in Newfoundland. In about 2014, they had a warmer summer, some of the ice melted away, and there was this really well-preserved big blue whale. This thing is about 180 kilograms. It's about the size of a small car, so some of you might know what a Fiat Bambina is, or maybe a little Mini. It's about the size of that car. It pumps 150 litres in 1 second. So 150 litres is the size of those big blue those big wheelie bins, I should say, so for your recycling or something in Auckland, if you know what I mean. So that's a lot of blood. It's heavy, the blood, and it's shunting it out of that heart in 1 second. And then it takes about 6 seconds or so to fill. So there's two things that the heart needs to do. It needs to pump and it needs to fill. And these are the two main things that can kind of go wrong with the heart. And we want to be able to use imaging and computer modeling to understand about what's going wrong with the heart. So you might have heard of heart failure, and I've sort of tried to have a go at naming heart failure. I need some help with this, so I want some people to help me with these names. So noi kore o te nākau, or maybe it's noi kore o te manawa. This is what heart failure is. So heart failure, normally what we see in terms of the imaging and the modeling of the pumping chamber of the heart, so the left ventricle of the heart. Here's a little animation here. Here's an MRI image cutting through the middle of the heart. Normally what we see is this nice pumping function and filling function of the heart. But there's two main forms of heart failure. One is to do with contraction. This is where the heart can't contract to pump enough blood out of the body. And in this case, this is what we call heart failure with reduced ejection fraction. Ejection fraction is the proportion of blood that the heart pumps out every cycle. Normally these hearts are quite big, and they've got lots of blood in them, and the walls of the heart, the muscular walls are thinner than normal. It cannot generate enough muscular force to pump that blood out of the heart. So this is a really common form of heart failure, and a lot is known about this. It was discovered, I guess, relatively early on, and there are really good medications. There's a lot that is understood about how to treat this condition. The other condition is heart failure with preserved ejection fraction. This is where the fraction of blood that is pumped out looks relatively normal when they measure it. The problem is that it's still working really, really hard. The walls of the heart are really thick, and this is a real problem because the heart cannot deliver enough blood to maintain the sort of needs of the body. And this affects about half of people with heart failure symptoms. So the problem with this disease is that there's not a lot that really is understood about it. It's got many different causes, and there's no good therapies for it. There's no cure, there's no treatments that are really effective in this form of the disease. And yet it affects about half of the people, like I say, with heart failure. So we want to understand about what are the differences, what are the mechanistic differences between these two forms of heart failure, and if we can understand those differences, can we understand about how to develop better diagnostic techniques and better therapeutic techniques to help with people with these conditions. So our game is to use imaging, and this is why we're here at Martyn, to work very closely with the communities that suffer from these diseases, with the expertise that they use, but also understand from an engineering perspective, because I'm a biomedical engineer, how can we use computer modeling, which you've been hearing all about this morning in different organ systems, the most important one being the heart, of course, and how can we use that to understand what's going on so that we can have a better idea about how to treat it? So we use MRI, and here's a picture of Taylor in the Martyn module. She works with, obviously, Paul, who you heard from yesterday afternoon, and that nerd, Dr. Dan. We were imaging with them on Tuesday, a nice small child because we are interested in contributing to the Tairāwhiti Child Wellbeing Study, which you heard about yesterday as well. So the idea is that we can get these really, really amazing images, and you've seen lots of amazing images over the last couple of days. We can get images through what we call the short axis, so this is cutting through the middle of the heart, or the long axis here, this is cutting kind of up and down, and we can get amazing information in all sorts of different planes, and we can develop these three-dimensional computer models of the main pumping chamber of the heart, the left ventricle, and we can understand a lot about it from a motion perspective, from a geometric perspective, and we can put these things together and develop these models and analyze the mechanical function, if you like. How much blood does it pump? How quickly does it do it? What are the dimensions? How big is it? How thick is the wall? All sorts of really interesting geometric and functional information that we can get from MRI. The other thing we can do with MRI is get even more detailed information about regional function. So rather than just the overall volume changes, we can look at laying down some of these magnetic stripes, and we call this tagging methodology. The actual tagging methodology here is called SPAM, so it's not that sort of meat in a can. I think it stands for spatial amplitude modulation and magnetization. I'll be testing you on that later as well. So the idea is that completely non-invasively, completely safe, no ionizing radiation, we can lay down these magnetic stripes and we can track those magnetic stripes throughout the cycle. We can see where do the individual pieces of tissue go when they start from the filled state to the contracted state. We can follow the motion, not just of the overall shape, but like we're putting little labels at all different points throughout the tissue, and we're following regional motion. This tells us about localized problems and localized areas of deficit of oxygen, for example. So this is a cool technique that's been around for a long time. It takes a little while to actually get these sorts of images, but it gives us really rich information. And so we can put that together with our models, and we can track all of these, we can track all of these little points and follow them throughout the cardiac cycle, and it tells us lots and lots of information. The other thing we can do, and there's going to be a poster, I think, in the lunchtime session from Aya, so I won't steal her thunder, but this is tracking the flow of blood within the ventricle now. So you can look at these lines here, the flow of blood as it comes into the left ventricle and out of the aorta. We can get a really good idea of what is happening to that blood and what looks normal. So one of the really interesting things about this is looking at the vorticity, how it sort of swirls around inside of the ventricle. Not all of the blood leaves the ventricle through every cycle, about somewhere between 50 and 70% in healthy people. Sometimes it goes down to 20% in sick people. But we can understand now what's kind of normal, what looks good, and what happens in terms of disease processes, particularly when we have problems, regional problems in the heart. So this is another technique that we can use MRI to be able to get access to. Instead of taking one image, it takes 4 images, and we can put all of that information together to get these really fascinating looking images, and we can understand things like kinetic energy, so all these sort of physics-based terms that some of you might remember from high school. We can really analyze all that stuff to tell us what's happening in the heart from a health perspective and a disease perspective as well. So you'll have to talk to Aya about this in the break. So what else can we do with MRI? It's a really fascinating technique, and I'll tell you why I'm showing about all these things with the heart. You heard a little bit about, I think, from Paul yesterday in the brain, about using this thing called T1 imaging. So it tells us something about the structure of the tissue. We can look at things like fibrosis and things like edema. So fibrosis, where collagen gets laid down in the muscular tissue. Edema, they may be swelling. So we can use this technique, T1 mapping on the left-hand side there, to tell us about, again, regional information around the structure and the tissue properties of the muscle. And on the right-hand side, I think Tor and Jeff maybe mentioned it as well. We saw some of this from Miriam's work yesterday, diffusion-weighted imaging. So we can use that in the heart to tell us about the muscular structure. So diffusion-weighted imaging, it tracks the sort of freedom of water to move within the tissues. And in this case, the sort of simplest way that water can move within the muscular tissue is along the axis of the muscle. So it tells us about the directions of those muscular fibers, and that's the direction of contraction within the muscle. Now, the really, really cool thing about the heart, and this is why it's the most important organ of the body, is that muscular direction actually changes its angle really steeply across the heart. So on the inside of the heart, this technique can show us that the muscular fibers are pretty much vertical on the inside of the heart. They go through to horizontal through the mid-wall, excuse me, and then they go to about minus 60 degrees with respect to that horizontal on the outside of the heart. So over about 10 to 15 millimeters, your wall thickness, you get this really steep rotation of that direction of contraction. And that's what gives rise to this twisting motion and the ejection of blood. So that's what the normal heart looks like, and we can use this technique to work out what happens through things like heart attack, what happens to that tissue, what happens to those muscular fiber directions. Turns out they're not very well organized and they can be in lots of disarray. So again, lots and lots of information that we can get from MRI imaging. And so why am I telling you all of this? Well, you can do this, and it is happening right here in the Martyn module all of the time, and we can put all of this stuff together in our mathematical model. So you've heard about digital twins from Peter this morning. You've seen some of the stuff that Tor's been showing you, and Jeff as well. We can put all this together for the heart and get a really good understanding of what's happening from a geometric, a tissue structure, a motion, and we can put that together with simple measures of things like blood pressure and some mathematics. So this is where the geek in me comes out. So I can say that Dr. Dan's a geek because I'm also a geek as well, and I will be testing you on this equation later. We can put it all together to say what's happening with your heart, because we can get all this information from your heart. So that's where we're heading with this sort of work. And why do we want to do that? Well, we can start to get a handle upon things that we can't measure. So things like muscle stress. This is the forces, the relationship between the forces and the geometry. We can get things like energetics. How much energy is your heart using throughout the entire wall of the heart, for example? We can get different sorts of biomarkers. So blood biomarkers tell us some things. We can get tissue-specific biomarkers now from these models, and we can correlate those with outcomes. So things like thinking about effectiveness of therapy, we could monitor that effectively, completely non-invasively, using these sort of techniques. But the problem with MR, one of the problems at least anyway, is it's really expensive, right? You've got a great machine here, but it might be a wee way for people to come here from, say, Tokomaru Bay and places like this. So what else can we do? How else can we get this information? Really, the workhorse of cardiology is ultrasound, echocardiography. So we're developing techniques now to be able to use machine learning, so where we get echocardiography from patients and MR from patients. MR is the gold standard in terms of measurement, but how can we use echocardiography, which is much more widely accessible, to get that same accurate information? We can take these measurements and bring them together and use artificial intelligence that Terry was telling you about a little bit about this morning to be able to train models to get really accurate information from ultrasound imaging. And that's what we've been doing, and it's not just on carts like this. So these are sort of wheelie carts. They're more portable than an MRI machine, but we can also do this using just a laptop. So here's Debbie. This was at the Gisborne AMP show about a month ago. Debbie, one of our researchers, is imaging Stephen's heart just using this little laptop type thing and generating models like this that we can use to get a real handle upon the function of the heart. So we were just doing that in the tent, the Martyn tent, like I say, a month ago, and there's a picture of Harry and Sam and the team, which we had a lot of fun talking to the public about. And so this is where we're really heading with some of this sort of stuff, is really understanding what's happening with individual hearts. And we can put this just on a web page. You can Google this when you get home, or maybe even on your phone. Google MedTech heart, and you'll get this three-dimensional model that you can kind of spin around. What we're going to do is take that imaging that we're doing in the lab in the clinic all of the time, put it on an iPad, show it to the people. Take the laptop, the ultrasound machine, up to Tokomaru Bay, take some images, stick it on the cloud, and deliver it back to their iPad, back to their phone. So have a go at this and just play around with it. You can spin it around, open it up, and understand about heart disease. Let's get that for every individual patient. That's where we're heading. So yeah, like I say, just 30 seconds to go. The idea is take the images, stick them through automated analysis, some motion analysis, some biomechanics, get these biomarkers out, deliver them through portable devices. That's sort of where we're heading with this type of approach. And it's not just great for patients, but it's also cool for kids. You know, we can stick this stuff in their hands, and we did in the tent a month ago, stuck an ultrasound probe in these kids' hands, and before know it, they're getting really good images, way better than I can do, just by enabling them with a little probe, that, you know, sort of thing that Terry was telling us about this morning as well. So this is our team. I just want to say thanks to all of our group. We're a relatively small group, but importantly, the patients that we work with, the cardiologists that we work with, and the research nurses that help us to sort of do this sort of stuff. So thanks very much.